Okay. Alright. Alright, continuing off with our instruction decoder for risc-v. I think like we're close to finishing up with logic. I mean, obviously there's like a lot of refactoring that needs to be done, like later. Like here, I could probably implement an enum class to get all this instead of having this huge if-else statement, but I need to learn how to do enums and all that stuff. So let's just get the simple logic down first for the rest of it. Okay, so we need to implement the U-type instructions, which is these two. So yeah, let's just try implementing the function now. Does say mu, right? So, or is that just not right? No, that just means upper. Okay, that makes sense. Since we're just masking off the smaller bits, so do unsigned int 2 and then just set it as immediately, and then set that as our value. We don't need a shift since we're just masking it off, so value, and it'd be pretty sure we could do like this, like FFF, and just mask it off, I'm pretty sure. Wait, hold up. I think this would be a proper mask for that, so we're just masking off the lower bits that are automatically set to 0, but the top bits we get it. Value. Right, and then it's pretty much just good to turn in. I'm pretty sure we don't need sign extension. Let me just get us a cloud. Mask is off, okay. Oh yeah, it's 20, my bad, not 12. Yeah, I completely messed it up, so. So now it should be that. There we go. And let's check it now. type. That was pretty easy. Let me just add this in the header file now. Add this function declaration in. Go right under here. Alright, there we go. And then add the logic in here. So what is that first instruction code? LUI. So LUI. The second one is IPC. So LUI. Our opcode was this. Hold up. 011 011. So our opcode is 0x37. And we should get our immediate value from get upper immediate, and this should be type u now, and we need to declare that in our inline variables as type u status u. Alright, that's good. Good so far. Then the last one here, which is IPAC. 011. That's for that one. 001. 001 01. Okay. Alright, got it. Oh shoot. Right? My bad. No. Hex 17. Hex 17. That is the name of it, right? AUIPC PC type U, get RD value, and then get upper. Okay, that should be right. Let's just give it all. Let's implement the main function now. Now we can actually see how it's written. Okay, let's see. So for this, it's like the name itself, and then let's see, wait. So we still do need the X because we're doing a register still. RD 1 comma, and it takes the immediate. So immediate is like that. Okay, that should be right. Let's get like an example bit string. Same for these two, so that should be right. Syntax error. Oh, my bad. Alright, there we go. good. Okay, so now we have loads left. Some loads. Alright, so since we implemented U type, now we just have the remaining I types. We've completed all like the types, same, but we need this one, the E break and the E call. Let's just get a list of what we have left. So E break, E call. Jal R. Got that. And then all these. Then after that, it should be done for 32-bit instructions. How does that look like for this? Okay, wait, so the memory instructions for I-type, we have the RD and the immediate. For I-type here, we have the RD, RSMAN, and immediate. So it's gonna be a bit different here. But no logic needs to change. It should be the same, pretty much. These are all I-types. Pretty sure. Let me get an example of JAL. Let's see if I can find it here. So JAL, the bits are different, so it shouldn't be. Does it have a func 7? No, it does not. So it can just follow I-type. instructions here. Same with that. Okay, these are interesting. I'm really don't know how to implement the eCall and the eBreak. But I guess just by looking at the opcode, but does that opcode like similar anywhere else? Just the opcode, bro. Their opcode is unique, so I guess I can just use the opcode. Equals eBreak. Okay. I don't know if I have to create my own type. I think that's the right way to think about it. So I guess I can start. Okay, let me start going back to that. Should be pretty straightforward for this one. Oh, did I run out of cloud credits or something? Oh no, I'm good. Okay. Wait. The syntax is different for JLR. Let me see. So it uses RD, destination register, register source 1, and the label. It's not that different. If anything, these are more different. I think that's what we'll do. Wait, hold on. I think that's what we'll do. We'll create the variables in our inline. I think that's a more easier approach than to mix and match. So we call this type load. We'll say this one will be type channel R. And then the last one can be type environment. Let's set the string as that. Okay, I think we can implement now. Okay, yeah, let's start with type load. So opcode is, let's find what the opcode is in hex. it's 3 in hex, so 0x3. What was the thing called? LB. LB. Type load. And what is the format for it? So it's the name and destination register. So we do need RD, and we'd need to get the immediate value. Let me take a look at what the actual thing is. What the bits are. So it's from 30 to 20, 31 to 20. Let's take a look. Which is exactly like the other one, SLTI. So yeah, it shouldn't change. So I'll just use the getIn function, I'm pretty sure. Yeah, I'll just use the getIn function for that. It should work. Swap code, so oh wait, we need to also check our factory. That's right. That's right. Byte unsigned. That one gonna be LH load half. And our func3 value is 2. Or 1, I mean, not 2, 1. It's 1. Next one is LH load half word unsigned. Load half word unsigned. Which our value will be 5. 0x5. Then we have 1 or 2 more, I think. Yeah, 1 more. Load word LW, which will be the opcode of 2, or func3 2. LW. So that works. Now we can put it in the main function. So if our type is type load, to be doing, let's see the format. So RD, so the registers do the same, and then immediately after will be the immediate, which will be the RS1 value. So we can just write inst dot in, then we need in parentheses inst.rs. No, wait, we can't do it like that, so we need to do another one. Inst.rs1. There we go. That should work. Or we can just do it like this now. Should be good. I'm gonna ask Gemini for a bit. An example, bit string for open risc-v. screenshot. It'll be x10, 8, x0. Oh, I know why. Because for all of these, we should be including rs1 as well. I totally forgot about that. Totally forgot about that. So I'm going to cover each one. Starting up here, yeah. Okay, everything has rs1 now for of type. Now it should work. If we take the string. Yes, it'll be x10 and then 8, offset of 8 for x11. Should be good. That. Now let's take Jalar. Let's do Jalar now. Just takes the RD in the label, so we have no need for rs1 anymore. And Jalar also takes those immediate, so I think we'll just stay with get immediate. That should work. Let's look at the code. So it doesn't have a functory. So no need for a functory. Wait. It does have a functory though. Why did it say it doesn't have one? Oh no, I was looking at the wrong one. That's my bad. I was looking at job. It does have a functory. Okay, that makes it better. I thought I had to rewrite something. It didn't have it. Upcode 6. Okay. Right. And a functory of 0x0, right? Yeah. Yes, should be right. Now we can implement. And the labels installed. Okay, perfect. Now we can try to get the string for JLR. Okay, we mean, not you need to use our pro one. We can just example bit stream for bar. Something's wrong. Dude, is that game like now thing like fucked up or something? Like, what's wrong with it? Oh, I guess Gemini was missing out. Dude, Gemini. Oh, interesting. Okay, there. Is it ours was not like fit to do it that way, so wait, X6. Not X0. Maybe it's wrong. Hold up. Oh, we still need our oh yeah. I don't know what I was thinking. Down. And what happened? Oh, what the fuck? Okay. There we go. Alright, now it works. We have the environment calls, which shouldn't take too long. So we have e-break and e-call. Okay, let's go. So for these ones, these last two, their opcode. Let's check out what their opcode is in hex. Their opcode is 73. And they don't have func 3. No, they do. It's just both 0x0, but oh, this opcode is different than that one. Wait, hold up. That shouldn't be right. That shouldn't be right. Oh, seriously? Oh, these, okay, these func 12 as well. We analyze against they have, okay, so they still have R, so these are 0, 0. That's interesting. That's the best way to distinguish between them. So I guess we don't need to write any new logic. It's the same logic. So just instead of this, wait. So interesting. So wait. So in this function, right? You're right. I think we can do like this. I think we'll just check it in here itself. We don't need the 12. I think this is just a better way of writing it. We'll see what Clark says. So we'll mask the bits to see what it is. Okay, yeah, that makes sense, because realistically, if we mask it for this one all 0, then it should just pass it as false. If not, then pass it. Okay, so alright, okay. I think, yeah, I'll do a nesting structure for this one. So we'll start with it being true, and then nest it inside after. I believe it was like 73, right? 1110011. 73, okay. 73, and both 3's go to 0. Oh, and then we will nest that in here. If value and we just have to mask the first 12 bits. So be like that. Which one is the one that's e-brake? That should be an environment type. And I think that's it. Yeah, that should be it. I'll get rid of these. And then just the else. Equal, right? Since if we mask these, if we mask it like this, all these will be put to 0, so that will evaluate to false. So with that if statement, it should be equal for that, for the else statement, and then e-brake for the if statement, I think. Let's just check this with Cloud. Hopefully that's right. Or any upper bits set rather than checking for a specific known value. Check with you later. I mean, technically, yeah, but like, there's no other environment calls unless they actually add it into the architecture itself. Then there won't be. But okay, I guess it's good to implement it anyways. Then if they ever do, which I don't think they will, but if they do. Well, I think we'll just go with that. So initialize it in here. What was it? Oh, no. We're not using value anymore. 0 to x1 and then else that else if yeah, I guess that's a better way of approaching it. Before I send that, I'll implement main function. So instance type environment, and it's literally just a name, right? For this one, it's literally just a name. So just the name. Okay, that should be right. Yeah, so just in case they add any other instruction, this won't break since it's explicit. That's there. Okay, so that's pretty much it. We covered every single instruction here. So now we have to see what the next steps are to actually go forward. But we will need to refactor a lot of this logic later. Just refactor it into like a more clean version. But at least we got the logic done, so that's the hardest part. So let's just give it a test. Example, bit string. Just want to test it. Bro, what's going on? Alright, so yeah, that one works for recall and then e-break. Okay, so that works. I don't need you anymore. Yeah, I guess we could do that, yeah. If none of these instructions work, and then yeah. Actually, you can type some random stuff. Invalid binary input, unknown instruction, yeah, that works. Alright, let's see what the next steps are. Okay. Okay, reads instruction that tells you what it is. An interpreter actually executes and maintains register state and update. Okay. Right, so now we actually need to implement it. Okay. Once your registers loads and stores need somewhere to read/write. Yeah, that seems like the next step, but that's gonna be quite difficult to implement because now I have to start new logic and understand new stuff now. But we have to do what it takes, you know. It's program counter. Okay. I mean, it seems like it seems like it was a pretty successful stream today. We finally finished like the basic decoding for everything. So yeah, I think I'm gonna have to do some more research about the next steps, learn some more stuff, and I think we'll just continue off tomorrow. So yeah.